Good morning, boys and girls, and welcome. Today we are going to talk about trigonometric functions and their inverses. Review a little trig this morning. Alrighty. Let's first start and let's review all of our trig functions and where they come from. Okay, so the three big trig functions are sine, cosine, and tangent. And again, these all come from right triangles, where sine is the opposite side from the angle over the hypotenuse. Cosine is the adjacent side over the hypotenuse, and tangent is the opposite over adjacent. And then there are those side labels right there. Okay. Then we have their reciprocal functions, cosecant, secant, and cotangent, which are just 1 over sine, 1 over cosine, 1 over tangent, or if you flip those ratios right there. And then also keep in mind that tangent can be defined as sine over cosine, and then again, the reciprocal function, cotangent, could be cosine over sine. So all trig functions are derived from a right triangle, but what we can do is we can take this right triangle and apply it to a circle, the unit circle, and that makes our life a little bit easier as we start to go around. So here's the basic idea is we have, our circle or unit circle where the radius is 1, and we have our different triangles at, 30, 45, 60, 90s, the main ones that we use. So that's how we kind of came up with the unit circle, and we applied our right triangle trigonometry to a unit circle. When we get to the unit circle to help us with some of the other, weird angles like pi over 2 and 0 and 3 pi over 2 that we can't do with our triangles, remember that the x-coordinate is the cosine and the y-coordinate is a sine. I'm sure we're all aware that it follows a pattern, 1, 2, 3. Like I remember sine is easy as 1, 2, 3. So it's 1 over 2, root 2 over 2, root 3 over 2. And then it just goes and bounces back and forth around the circle. Also remember that in the first quadrant, all trig functions are positive. In the second quadrant, just sine and cosecant are positive. Third quadrant, tangent and cotangent are positive. In the fourth quadrant, cosine and secant are positive. ASTC, all students take calculus, is the acronym commonly used to remember that. Okay, then we had some identities that you need to know, namely the Pythagorean identities. Sine squared plus cosine squared equals 1 is like the most important. We got to have this one down. There is also variations of this that you need to be aware of, or at least know how to find. Like I don't ever remember what they are, but I know how to get them when I need them. If I take sine squared plus cosine squared equals 1, and I divide everything by sine squared. Okay, in the front, that's going to, sine squared divided by sine squared is going to give us 1. Cosine over sine is cotangent, and 1 over sine is cosecant. So this gives a new Pythagorean identity. 1 plus cotangent squared theta plus cosecant squared theta, or equals cosecant squared theta. So you need to know that, or again, know how to find it the way I just did right there. And then the other one, if we divide everything by cosine squared, so let's get rid of that sine squared now and divide by cosine squared. And this is going to give us sine over cosine is tangent plus 1 equals secant squared theta. See, there we go. We got it. Again, you need to know these three identities. You don't have to have them all memorized. If you know the sine squared, you can always generate the other two. But these are three identities that the AP exam will expect you to be familiar with. Okay, the three Pythag ones. On top of that, the other one that we need to know that you used in trig pre-calc, but you did not have to have memorized, I'm telling you it's going to be very important this year. You'll see it pop up all the time, is the double angle for sine. Sine 2 theta is equal to 2 sine theta cosine theta. You're going to want to have that down and memorized as well. So these four are the four that we need to know. Anything else, they'll either give you if you needed it, which is not very often, or just know that you can go and look it up. Okay. If you need other trig identities, you can either look online and find them. Just Google trig identities, or if you look in the front/back of your book, I believe you will also be able to find them there. Okay, the last thing we need to talk about is our inverse trig functions, sine inverse, cosine inverse, tan inverse. I guess you could also talk about cosecant, cotangent, and secant inverse as well, those ones. But before I do that, I want to do a little kind of tie-in with what we talked about earlier. When you take the sine, you have to take the sine of something. Okay, we're not multiplying here. You're taking the sine, we call that the argument. And so we're taking the sine of some theta, some angle. And when you do that, you're going to get a ratio of the sides, right? Opposite of our hypotenuse. Okay, so when you take the sine of the angle, you get a ratio, I'm going to say. The sine of theta is going to equal a ratio. All right, now, taking this and applying to the inverse. When we find the inverse, what we're doing is, I'm taking the inverse of that ratio, and I'm trying to find the angle. Okay, we're trying to take the inverse of the ratio, and that will give us the angle that gave us the ratio in the first place. All right, so sine inverse of the ratio, that's why I'm using x over here. Sine inverse of x, cosine inverse of x. I'm not using a theta because you're really taking the inverse of that ratio. Okay, so I think that idea, the interplay between the ratio of the sides and the theta and how we use these two functions, I think is important to kind of understand. All right. The other thing to understand about sine inverse, cosine inverse, tangent inverse is also a naming thing. In trig pre-calc, you probably mainly use sine inverse, cosine inverse, etc. But know that equivalently, we could say arc sine, arc cosine, or arc tangent. Arc sine, sine inverse, those are the same things. In calculus, because that little -1 will cause us issues sometimes notationally, you'll see it's very common for us to say arc sine instead of sine inverse. But they mean the same thing, so know that they are the same. You can use them interchangeably. Okay, then lastly, when we're talking about the inverse of these functions, remember that if we looked at the entire function, then it's not a function, right? If you look, for instance, if we looked at sine, there's a quick sketch of our normal sine wave. We could take this now and make it symmetric, reflect it over the line y equals x to get the inverse function. So if I do that, sine inverse would look like this, or something kind of close to that anyway. But you got the sine wave going up and down the y-axis now instead of on the x-axis, which, again, this is now not a function. So this is a quick, again, justification why on these functions we had to restrict their domains so that the inverse would be a function. So we restrict the domain from -1 to 1, those are the only values we can use, and then we say that the range then you're going to use with those is from -pi/2 to pi/2. The angles that you're going to get out when you take the arc sine or sine inverse of that ratio, -1 to 1, is -pi/2 to pi/2. And we use that, that's the fourth and first quadrant, but we use the -pi/2 to pi/2, so it's a continuous interval. That is the same for tangent and tan inverse. Remember, those are always in the first and fourth quadrants as well. -pi/2 to pi/2 for the angle you're going to get out. And then also for cosine inverse or secant inverse, we use the first two quadrants, quadrant 1 and quadrant 2. And so that is from 0 to pi is the angle you're going to get out. So again, keep that in mind. It's always got to be on that interval when you do arc sine, arc cosine, or arc tangent, or any of the inverse functions. Okay, so let's do some examples. First I want to find the sine of 2 pi 3. This is why I do my trig quizzes in class. We need to have these on the top of our head. We can't sit here forever trying to figure out what this ratio is. When I do sine, I think it's easy as 1, 2, 3, and I think of my unit circle, and I think of the first quadrant. So at pi/6, it's 1, pi/4 is √2/2, pi/3 is √3/2. And again, I do that because anytime now it's over 3, like this is 2 pi over 3, I know it's going to have the same ratio as pi over 3. So I know my answer has to be √3/2. And now I just got to think, what quadrant is 2 pi over 3 in? 2 pi over 3 is in the second quadrant, so this must be in the second quadrant. Sine is positive. All students take calculus. So I know that this has to be positive √3/2. I would say that this is the thought process you want to be going through to quickly get to a sine, cosine, tangent ratio. Okay, next, if I want to find the secant of 7 pi over 6, the first thing I think of as secant is the same thing as cosine. It's just 1 over cosine. So now I want to find cosine in the first quadrant. So I'm going to think about that. So I'm going to erase these ones here, and I'm going to redo my unit circle. Cosine goes 3, 2, 1, so √3/2, √2/2, 1/2. And again, this is 7 pi over 6, so I need to know the pi over 6. So at pi over 6, again, it is √3/2. So I know this is going to be 1 over √3/2. However, again, 7 pi over 6 is in the third quadrant. And in the third quadrant, cosine is negative. So this is going to be 1 over negative √3/2. I got to think about all the different aspects. And then now, again, it's 1 over, so I need to flip this to get secant. So it's -2 over √3 or -2 √3 over 3 if I rationalize my denominator, would be my answer. Again, I don't care. You could write it either way for me, -2 over root 3 or -2 over 3 over 3. The book says the answer is -2 over 3 over 3. So you, again, practice matching the book, I would say, when you get these kind of answers, but that's how I'd find the secant of 7 pi over 6. Okay, next, this is one of my favorite parts of trig pre-calc was proofs. We want to prove that tan theta is going to equal sine theta over cosine theta. All right, so remember when you do a proof, you want to start with the more complicated side, and so I'm going to start on the right-hand side, and I think I'm going to go back to our definition of sine and cosine. Sine, again, is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So just rewriting my sine over cosine. And now, again, we're really just dividing these things, right? These little fractions just mean divide. So if I divide fractions, I'm going to skip, flip, and multiply. So skip the top fraction, leave it exactly the same. I'm going to flip the bottom fraction, and then I'm going to multiply these together. And so when I multiply these together, I can cross cancel here, and the hypotenuses can die off. And so we are left with opposite over adjacent, which is the definition of tangent. So we just proved that sine theta over cosine theta equals tangent theta. Perfect. Okay, for our next one here, we're getting into our inverse trig functions. We want to do cosine inverse of -1/2, or arc cosine of -1/2. So again, I'm going to think about my unit circle. And again, it goes root 3 over 2, root 2 over 2, 1/2, 3, 2, 1, right? For cosine. And so I know because I'm doing cosine inverse of -1/2, and 1/2 is a pi over 3, I know that this angle is going to have to be over 3. Again, we're taking the inverse of that ratio, and we're trying to ask ourselves, what is the angle going to be? So the angle, since it's 1/2, is going to have to be, an over 3. And because it's negative, then, I know, again, cosine inverse is between 0 and pi. That angle has to be between 0 and pi, because it's in the first or second quadrant by our restricted domain and restricted range. So the over 3 that is going to be negative is going to be in the second quadrant, so this has to be 2 pi over 3, and I'm only going to get that one answer out. Okay, so cosine inverse of -1/2 is 2 pi over 3. All right, and then lastly now, number 5, we want to do the inverse functions, but with an expression instead of, numbers. This is where it got to be fun, if you remember back in trig pre-calc. So again, this is where I think it really helps remember that we're doing the inverse of a ratio and trying to find the angle. And when we do, like, say, cosine, we're taking the cosine of an angle, and we're looking for that ratio. Okay? So when I do, I would start this like order of operations. I'm going to start by looking on the, inside, and I'm going to start by trying to evaluate sine inverse of x over 3. Now, because it's x over 3, I can't really find out what that is. But I can, again, think back that, hey, this right here, this x over 3, that is the ratio. So let me set up my triangle. The ratio for sine, again, is opposite over hypotenuse. So if I look at sine inverse of x over 3, that is telling me that the opposite side must be x, and the hypotenuse must be 3. All right? If that is my theta right there. On the next part now, again, I'm really going to look for the cosine of some theta. And it's that same theta that we're dealing with up in our triangle right here, and we're trying to find out what our answer is. So, cosine is the adjacent over the hypotenuse, and I don't have the adjacent side here, but if I have the other two sides of a right triangle, I could go ahead and solve for the adjacent side. So x squared plus b squared equals 3 squared, where b, again, I would say is this adjacent side, and now I can go ahead and solve for b. So b squared would be 9 minus x squared, and if I square root both sides, I get that b is the square root of 9 minus x squared. All right. So now that I know this side, I can actually go find, even though I don't know what x is, I can go find the cosine of this angle. The cosine of this angle, again, is the adjacent square root of 9 minus x squared over the hypotenuse. And there we have our answer. All right, so that's it for today, boys and girls. If you got questions, again, hit me up as usual. See you later, and have a great day.